Hi, welcome to area between two curves. Very simple little lesson here today. We have two functions, f and g, bounded by a domain a and b. And we just want to find the area between them. Now, if you notice, what I drew here is I drew a line connecting f and g. Well, secretly, that's not a line. It's a rectangle. So what we're going to do is we're going to find the area of this infinitely tiny little rectangle. So to do that, let's blow it up. So I'm going to blow it up like this. There it is. There's the area of this little rectangle right here. Now this rectangle, it has a height and it has a width. Well, the height is pretty simple. So to get the height of my rectangle, all I'm going to do is just going to take the top function minus my bottom function, f of x minus g of x. Like so. Well, what would the width of our function be? Well, that's how wide this is. Remember, this is calculus. That's a very thin width right there. So skinny, we call it dx. It's infinitely thin. We call it dx. So, how can I find the area of my rectangle? Well, very simple. To get the area of my one rectangle here, it's going to be f of x minus g of x, the length or the height times the width, dx. Well, that's the area for just my one rectangle. But remember, we have infinitely many rectangles, very skinny. And what we want to do is we want to find the area of each rectangle and add them up. So we want to find and then we're going to find the sum of all those rectangles. Now, remember, because there's an infinite number of them, to get the exact area, we take the antiderivative of our area, f of x minus g of x dx, and we're going to integrate that from a to b. And this will give us the exact area under that curve. Now that was in terms of x. Well, what if we're in terms of y? Well, if we are in terms of y, instead of drawing a vertical rectangle, we're going to draw a horizontal rectangle, like so. And again, we're going to blow it up, just like my phone. It keeps blowing up. People keep calling me. Hey, when are you going to make another video? Well, here I am, another video. So this rectangle right here will have a width of dy, because it's very thin, and it's in terms of y this time. How do I get the length here? Well, in this case right here, we're going to go with the right function minus the left function. So the right function is going to be f of y minus the left function, which is g of y. So again, the area of our one rectangle is f of y minus g of y, see we're in terms of y, dy. So to get all the rectangles, the area of all rectangles, there's an infinitely many of them, we're going to integrate our area, f of y minus g of y dy from a to b. In this case, a and b are arranged from low to high. And there's how you would get the area of all those rectangles in terms of y. So here's a hint for you. Whoops, messed up there. Here's a hint. Okay? In order to find out which one goes first, f or g or f of y or g of x, or whichever one goes first, f of x or g of x, here's what I always tell people to do. The hint, what you're going to do is always put the larger function first. And what do I mean by that? Well, if it's in terms of x, f of x is larger than g of x because it's on top. It's higher up, so it's larger. In terms of f of y, I'm going to put the one on the right first because the right side numbers are bigger or larger than the numbers on the left. So it's basically our number line right there. See? Larger x values, smaller x values to the left. So you always want to put the larger function first, which is why we put f of y minus g of y. So in terms of x, what we're going to do, it's going to be the top function minus the bottom function. Notice, and we're going to make a vertical rectangle. In terms of y, it's going to be the right function minus the left function. and this is going to be a horizontal rectangle. So let's take a look at an example here. We have a parabola and a line, and we want to find the area bounded by this parabola and this line. So the first thing I'm going to do is I'm going to sketch it. I want to see what it looks like. And to do this, I'm going to go, ready, let's see here. It's 3 minus x squared, so there's 3. It's minus x squared, so it's opening down. There's my parabola. Next, I want to graph the line y equals x plus 1. Well, there's 1. And it's a negative slope. I don't know what this looks like. I'm not going to be perfect. I'm not looking for perfection here. And there it is. Now, I'm looking for the region bounded. Well, what does it mean to be bounded? It's kind of like you're trapped. If you're in one region, you would be trapped. You can't get out of it, like being in a box or something like that. So that's what means to be bounded by something. You're not able to get out of it. So if I'm looking for the area bounded, I'm not going to pick this region because I can get out. I'm going to pick this region because take a look. It's surrounded by functions. So this is the region we're looking to find the area in. And I'm going to shade it because I'm the Slim Shady. All those other Slim Shadys, they're just imitating. So that's the area that we are looking for here. Now, I am in terms of x. So my functions are in terms of x. And because of that, I want a vertical rectangle. So if I'm looking for that area, my rectangle I'm going to draw is going to be vertical. From the top of the function to the bottom of my function. Notice, I don't cross the x-axis, I stop at the function itself. So when I draw my rectangle, there's my rectangle that I just drew, I'm going to blow it up. Now, I do want to see this. This is a requirement. Remember, it has a width. It's change in x. The width, the length down here is a change in x, and it's very tiny. dx. It's dx thin. It's dx small. dx is tiny. And to get the height of my rectangle, that's this part right over here, because it's a vertical rectangle, my rule says top minus bottom. Well, the top of my function is the parabola. It's 3 minus x squared minus, and the bottom one is negative x plus 1. So if I want to, so I can simplify that a little bit by saying this is going to be what? 2, minus x squared, and let's see here, plus x. So to get the area of my one rectangle, it's going to be this 2 minus x squared plus x times dx. It's the length times the width. Remember, we're dealing with infinitely tiny little rectangles here. That's all we're doing. Tiny, skinny little rectangles that have a length and they have a width. The length of my rectangle times the width of my rectangle. Now, to get the area of all of them, I'm going to integrate that from 2 minus x squared plus x dx. Now, the problem is I don't have a domain yet. So how can I find this domain? Here's my A, here's my B. Well, how do I find A and B? We have to solve. We have to find out where these two equations are equal to each other. So to find the domain, it's where they meet. So to do that, I'm going to take my 3 minus x squared equal to negative x plus 1. I'm going to bring the x squared over, so I get x squared minus x, what's that, minus 2, set that equal to 0, and I can factor it. X minus 2, x plus 1 equals 0, so I get 2 and negative 1. There's my domain. Smaller number goes on bottom, negative 1 to 2. And this will give me the area of my function. So let's go ahead and calculate that exact area. We're going to get the exact area here. To do that, I'm just going to integrate negative 1 to 2. This becomes 2x minus x cubed over 3 plus x squared over 2. Applying the FTC, f of 2 minus f of negative 1. I just plug those numbers in. I get 4 minus 8 thirds plus 4 over 2, so plus 2, plug in negative 1, minus 2, plus 1/3, and this becomes a positive 1/2. And if you simplify this, you get 4.5. So the exact area underneath this curve is 4.5 units. Well, that's the end of part 1. Join us in just a few moments for part 2, and we'll finish up the notes here. Thank you.